our 9th festival, the Data Science Festival May Day edition. My name's Jackie. I'll be emceeing with you today in this room. And I really want to just give you a big thank you for coming out to see this community thrive and help us continue to build that. What we ask for today is for you to switch off your phones or put them on silent. You're going to see a schedule of different talks in different rooms in a booklet in your swag bag, so please take a look at that. If you have any questions, please find a Data Science Festival team member. We're going to be wearing this lovely shirt. You might find a couple other variations as well. And there is also free water at the back if you want to refill at any point. So the Data Science Festival is a celebration of all things data. We aim to connect the tech community and foster the sharing of knowledge, inspiration, and ideas. Just a reminder that all of the talks are going to be recorded, so if you miss one, you'll be able to catch up on it later and on the Data Science Festival website and the YouTube channel. If the room is full, just make your way to another one. Please don't worry. This event is free to attend and built by the community. Without the help of our sponsors, we couldn't make this event happen. And thank you to the Data Idols, BSI, Unidays, Future Coders, Superlinked, Iris Informa, SDG Group, Digitas, dunnhumby, and Vida, Snowflake, Create Communities, and Code Node, who provide us with this incredible space for this event. Thank you again for attending today, and we hope you have a great day. Also, check out the back of your booklets. You're going to see a portion of a popcorn competition. So if you want to win 500 quid in cash, you'll find that midday downstairs with a poster of what to do. The free popcorn on the back will be located in the festival zone and will be available from 12 to 5 today. Now, our first talk is by György Móra, who, with the title 10x the retrieval quality of your vector search. So, György is a chief architect at Superlinked, based in Budapest, Hungary. He's a software engineer by trade and started his career on machine learning and information retrieval academic research projects. As a contractor, he built search and recommendation systems for an online presentation tool and worked on various data science and engineering projects. Before joining Superlinked, he worked on a large-scale machine learning system for fraud prevention at MasterCard. He is a better data scientist than the average software engineer and a better engineer than most data scientists, with a solid drive to make their lives easier. Since moving to a house with a garden, left with little free time, he did enjoy film photography, hiking, and foraging for mushrooms. So, welcome, György.
Thank you very much. Hello and good morning. So, last year, you have seen Daniel, our CEO, here. And since then, there are 2 changes. That's why I'm here and not here. So the first change is that we got founded. We raised $9.5 million, and therefore the company moved to the United States from the UK, and therefore he's there. And the second change is that we open sourced the interactive part of our product, and which means that we are not talking about plans anymore, but we are more like talking about the things we built and how we imagine using vectors for various tasks. And why vectors matter. So why it is important to build systems which are good at calculating vectors. You can see a lot of hype around retrieval augmented generation and search tools and recommendation systems. And also you can use vectors to analyze content, to analyze your users, to analyze documents. If you can turn anything into a vector, then you can search easily because you can turn your search terms also in vectors, and you just find the close points in the vector space, and then you return them, and that's your search result. Similarly, if you think about reg, you have to do a search. Actually, the search terms are not provided by the user necessarily, but it's an unstructured data what you try to process. You process it in a vector, you go to a knowledge base. The knowledge base is also organized into vectors, and then you find the closest vectors, and that's how you do the enrichment, the knowledge retrieval for your reg. So vectors are everywhere. Big players are using vectors. Spotify, obviously, they are in the recommendation business. You listen to something, they turn everything into vectors, and then they say, yeah, we are building on top of vectors to recommend you the songs you most likely like. Google, they are very big players. They do everything, basically, and they say vectors are multi-tools. They are like the Swiss Army knife for them to do data and machine learning. At Meta, they do all kind of embeddings, and embeddings also mean vectors, and they are kind of in the retrieval business, so to have good quality retrieval based on vectors, they have to understand how vectors work and how to build them, how to search in vectors. Airbnb is in the personalization business. Vectors are also essential for them. So this means that big players are already using vectors. Vectors are a thing in the industry. But they have huge capacity. They have big teams, hundreds of thousands of engineers working in these things. Because it's not easy. So you have complex data, for example, this housing advertisement or housing data. There are many things in this picture or many things in this page what you wanted to process and you wanted to search for and you wanted to incorporate into your system. So there's like an image. You have to embed the image. There are description. There are structured data, categories, numbers, numeric data. Also, you can have usage data. So how many people like this listing? Whether the user you are helping to find a house interacted with other properties. How the interaction was, that they liked it, they disliked it, what you would do with that information. So how you incorporate into that information into search vectors or vectors what you can search for later. So this is not an easy task. And I'm sure that you have seen demos for embedding text, and you can do like amazing things with language models nowadays. So you take an unstructured data, some text or image, and you turn into some vectors, and you search that vector space, and you get amazing results, and it's like a 20-line long notebook. But to actually incorporate all the data you have, especially if you're in an enterprise environment, so you are a big company, you have a very complex data model, maybe graphs, and it's actually not trivial how you can turn it into a useful system. So LLMs alone won't solve the problem. So that demo you've seen is very good for like showcasing the power of the language models, but that alone won't solve the problem. One way to deal with this is building custom models. But I think most of you know that it's not very easy to build custom models on top of these features. Also, to incorporate a custom model into a company's business, core business, is also not a very easy thing. So I'm doing it at MasterCard, and especially in the financial sector, it's not a very trivial thing to do. So the best would be to use like pre-trained models, somehow combine them into a system, do the fine-tuning on it, and then release it into production. That's also a key part, because it's not enough that it works in an experimental environment, but it's also essential that that you can quickly release it into production and make the value out of it. So another component or another aspect of this thing is the vector databases. So there's a big uptick on vector storage and vector retrieval. All the big players, other databases which are not primary vector databases, now they're offering some kind of vector capabilities. Some of them are offering very good vector capabilities, some of them are offering less. And so we compiled at Vector Hub this huge comparison table. Maybe you have seen it. So we try to find all the features, what we think is very important for building a performant and flexible and very good vector-based system. And then we evaluated these databases based on that. So that's a huge, huge matrix. And so it's easier for you to pick the right tool for your task. It's open source, so you can also contribute if there is something missing or you think there is an error or mistake, then you can extend it. So there is a need. The big guys are doing it. It's hard to do. There is lots of options for storing and retrieving your vectors, but then who will do the computation? So you can see that there are actually solutions for that, or they try to solve this thing. But this is not a comprehensive solution. This is basically the vector analogy for the LLM demo. So it is basically an LLM demo inside the vector database. And it doesn't deal with deployment. It doesn't deal with complex data structures. So there is room for something which can do that. And we hope that something is what we are building. So we call it a vector computer currently. And so the idea is very simple. You have all the structured data. You have all the unstructured data. We don't do data processing that much. So we think that there are beautiful systems for that. You do the data processing, the data cleaning, the enrichment, whatever in those systems. And then we ingest your data, the unstructured and the structured data as well. And then we create the vectors based on the definitions you made. And then we feed into the VectorDB of your choice. So we need certain features to be available on the vector database to be able to integrate it. And partially, that's the reason why we are compiling that big matrix of capabilities. And then your AI applications can interact with it. It can even feed data into it, or it can query it. So we provide a query interface as well. So that's the mission, right? So take everything, make vectors. Very, very simple. We want it to be that orange arrow. Okay, so again, what you can use vectors for. So you can use for recommendation. Recommendation is when you have a piece of document or a user or some entity which was in the database before, and you would like to find another entity which is very similar to it. So you find all the similar vectors, and then you return it, and that's it. Search is very similar to that in the vector space. The only difference is that you don't have an entity already in the database, but you have to create one on the fly from the user submitted information. That's a bit of a hard part, because if you ever used LLMs or these kind of systems, they are not very, very fast. So it is hard to build a system which is very responsive, also not very expensive to operate. So that's a challenge, and we are trying to help in that as well. Classification, which is a bit of a surprise, but it's a kind of standard practice in a lot of places. Like I've seen credit card fraud systems working this way. So how this works is that you have the training instances, so you have vectors in the database, and they are labeled, so it is labeled data, like classic machine learning, supervised learning setting. You have the good guys and the bad, or the good transactions or the bad transactions, and there is a new transaction, for example, coming in. You vectorize it, you create the vector, you throw it in the database, and you see the immediate neighborhood. So you basically do a KNN search, you return the top 1,000 transaction, and you say, okay, half of the transactions were bad, so I assume this transaction is not so good either. So this is a way to do clusterization with this setting. So you can say that the vectors are really features for clusterization. If you wanted to do some analysis on your data, you wanted to see who are the outliers in the data, you can also do analytics with this. So fancy features, basically. Fancy name for features. Okay, so maybe the last one, like using it for classification, is a bit like stretching it. So some people might say that yeah, okay, so you are the guy who has a hammer, so thinks everything is a nail. But the fact is that if you think about a proper solution, sometimes it would mean training a big machine learning model and maintaining it and dealing with like drift, semantic drift, feature drift, all kind of problems and issues. But what is the goal? The goal is usually to satisfy the business need. And it means that a less than perfect solution, which is scalable, fast, and easy to implement, is probably worth more than like shooting for the perfect solution. So that's one aspect of why I think this hammer was swaying around. And the other thing is, so you can probably recognize this classic machine learning lifecycle thing. I think this is true for all kind of data projects. So there is this business goal setting phase, and then at the end you evaluate whether you met your goals. And I think one crucial part is what the data scientists probably don't think enough about is deployment. So you can have your notebook, which is very nice, and you measure good results on it. But then how it will go into production, how the user will interact with it, how it will be performant, cheap, and maintainable to operate. And that's usually it's not a trivial thing to do. Many companies are struggling with it. So I was working for a company who had like a team of 50 engineers for half a year integrating each and every model after it was built. While our department, it was basically bumping a version number on an asset. So it's hard to do it right, and it needs a lot of investment from both sides. So that's what we are trying to also help, because what we are shooting for is that you declaratively define what your vectors looks like, what you wanted to put in your vectors and how, and then you can experiment with it in an experimental, we call it interactive version of our software, and then you say, okay, I'm done, I think this is good, let's ship it. And then without changing the core definition of your vectors, just changing the boilerplate around it, where the data is coming from, where the data is going to, you can just deploy it without any changes. So that's the promise we are trying to do here. So what currently and in the near future the hammer can do? So you can obviously do some text embedding. We have a let's say interesting approach on time, because if you embed a text into a vector, the text doesn't change. It is there. So it will be the same text tomorrow, and the meaning of the text will be roughly the same tomorrow. But it's not true with time. So time changes even you don't do anything, because time goes forward. So if you say that this listing on the website, this house listing is 1 day old, tomorrow it will be 2 days old, and after tomorrow it will be, again, 3 days old. So without recalculating the vectors every single minute, it's hard to actually have a real-time sense of time. So you cannot really query things which are just added 5 minutes ago, or 10 minutes ago, or 2 hours ago, without changing everything. So we figured out a way to do that. It's not very straightforward. We are wrapping our mind constantly, and yeah, so it's endless debug sessions and stuff like that. I will show you in the code. Numeric embedding, it is also not that simple, because sometimes you want the number to be as high as possible, like rating of the property or rating of a hotel room. You want 5 stars, or you want 9.5. But sometimes you want it to have the number close to your target number as much as possible. So for example, the price of the house or the price of the hotel, you don't want it to go lower than that much, and you don't want it to go higher. So it's a different similarity. So here we are basically talking about similarities, how we will encode this into a vector, so similar vectors will be close to each other. And I think the most interesting part is combining different vectors. So the combination can be that you take the text, you take the recency, and some categories and numbers and whatnot, and you concatenate them into one big vector. There are all kinds of problems arising from that, normalization, for one thing. But this is one way of combining, and this is also very exciting. The other combination is when you have multiple vectors and you want to combine them. Why would you want to combine multiple vectors? So for example, there is a user who interacts with listings, like housing listings. Then the houses have a vector, and the user have an interest vector, let's say. And you wanted to aggregate those visits into the user's interest vector. And there can be all kinds of questions like, yeah, I don't want it to consider a visit 3 years ago on the website that much, but if I don't have any other information, I really wanted to consider that. So how you aggregate is also not very simple, and the data scientist would probably want a lot of freedom about how to aggregate those. And that's what we call handle events. So an event is when somebody interacts with the system. So two entities, a user entity and the document entity, or a user and the housing entity interacts with each other. And the last one, what our system currently can do is weighting the vector parts at query time. So instead of weighting the vectors and combining them and putting into the database, we can change how important each part for every query without recalculating the vectors. So this is actually not very complex, but we haven't talked about it for a long time, so it surprised us how easy it was to achieve it. So I will show you examples how that works, but it's a very neat thing, and you can play with the system, and you can come up with the weights you want. But if something is changing or there's a new usage, then you can adjust it for each and every query even. So I was talking about the data scientists and what they want. So I was a data scientist before, and what I wanted to do is very rapid prototyping, experiment with things. What I never wanted is do the actual data cleaning and do all that stuff. And at a big company, something, it's the best when that's taken care of. You store the clean data, and then you don't do that over and over again. So that's kind of our approach, that we have an interface in our system where the clean data is coming in. You type it, so you tell like how it looks like, and from now on everything is very clear and tight and neat. And then you can focus on the science part. So how my vector looks like, what are my weights, what are the parameters for those vectorizers and embeddings and whatnot. And how we achieve that is that we call it a DSL. It's not a real DSL because it's in Python, so this is basically a Python interface. And we developed it together with data scientists, so it doesn't look like what we would do as engineers, but it looks like what they like in Pandas or other tools, so it satisfies their needs. And then we built a layer beyond it, which actually makes sense and easy for us to work with. So that was our approach of the user interface. Okay, so actual code. By string programming, I mean that we don't want it to. If it's in Python, why don't use Python? So Python has typing, Python has variables. So why you are referring to data with strings, like names of the columns in a data frame or whatever. So our approach is that we do schemas. Like this is a very simple schema. There's only a string, which is the body of a paragraph, so it's some kind of document paragraph or something. And then what you do is that you say, okay, so I would like to define a text similarity space from that thing. I define what models is doing the embedding, and then I create an index. So that's the most simple thing you can do. The index is actually like the vector, defines the vector and defines how it will be stored in a vector database. So yes, but data scientists also want features. So we are focusing on how we can integrate these kind of things very seamlessly. So you say, okay, but my model wants chunking. So yeah, then we added this chunking thing, and then we handle the chunking beyond the curtains. So it means that when you retrieve an object, then you don't have to deal with, yes, this is a chunk of an object, please give me the object. So we handle all of that because we know that this is a piece of a bigger object. And yes, so you can add time to the mixture. So this is a recency space. I will show you an example of this movie database thing. So you can have period times. I will show you later what they mean. But basically, you define like what time periods your amortization works. So if it's 4 years, that's like linear amortization in 4 years, then in 10, and then in 40. And then there's this negative filter. So after 40 years, everything is not very similar to your search term, right? So that's basically saying that I don't care about things after 40 years. It doesn't mean that you filter them completely out. They are just weighted down. So we have this paragraph schema, we have the user schema, and you can mix it together. So you can say, in this space, I would like to have the paragraph body and the user bio, which means that you can search by the user's bio in the paragraphs. So you can say, give me similar paragraphs to this person's bio, or vice versa. That's what it means. Query interface, you define the query. In the production, you want, so this is not like a SQL system. So you have to define the queries before, because there are implications of the queries. We have to be sure that certain things are indexed in a way, so it's not that easy that you can query anything. You have to define the query, but everything can be a parameter inside. So all the numbers and all the knobs you can turn later. So this is to find the user, find similar paragraphs to a user, and you give the user by user ID. So this is basically a recommendation system. You recommend the document based on the user. I was talking about deployment. So deployment is hard, but this is the boilerplate for the experimental framework. So this is the in-memory source, the in-memory executor. These are all living in your notebook, and you can play with it. You just put data into the source, so you can consume a data frame, and then you can just print your results. So that's the system you're playing with, and this is the boilerplate which is added to basically this. So this is your dog, this is your graph definition, this is what you wanted to do with your data, this is how your index looks like, and this will be the same in the production system. This is not, this is the notebook boilerplate. So the dog stays the same, and this is how a production system would look like. So you say, oh, I would like to have a REST API. That's where the data will coming in and the queries will coming in. And then you will have a Redis for storing the entities, so storing the vectors. And you have the online executor, which can take REST sources and fire up REST interface. So that's what the data engineers will define. Obviously, there are like parameters everywhere, like where is the Redis, what is the password, but that's not that exciting, I guess. Okay, so let's see it in action. Yeah, okay, very good. So this is done by one of the data scientists, and he decided that he will take the Netflix data set and he will show in a notebook what the system can do, and you can play with it. And this is a very important part, I think, or it made us very happy when we first being able to do that, because that means that we released the system, and it is open source now, and so you can just simply type this into any system, and you can start using Superlinked. Okay, so we do some imports, obviously, and as I said, we don't do the data analysis part, so the data scientists did some data conditioning here and changed some formats and whatever. And this is how the data looks like. So there is a description of the movie, there is genres and the title, and when it was released, basically that's the important information. Every line has an ID. That's also a system requirement in our system. Each piece of data travels through the system with an ID attached. So this is the distribution of the movie titles. Sorry, not the movie titles, but the release dates. And so do the schema. So he wrote the schema, like, oops. So like description, title, release, timestamp, nothing surprising, the same things. And then he defined the spaces. So he used text similarity for encoding all the textual content. And this is the recency space. You see in the exact same period times. And then he creates the index. So he says that I have these spaces, the description space, the title space, the genre, and the recency, and I wanted to create one index out of them. That means that that's one vector. And then he defines the queries. So there is a simple query. This is simple because so all the weights have parameters, but the query text is the same. So you use the same query text to query the description, the title, and the genre. And then we will return the top n. And this is a more complex query. The complexity comes from you have different parameters for each of these fields. So we load up the data frame. We do the boilerplate for the notebook, and we run the executor, and then we ingest the data frames. And so this is what your amortization function looks like for the recency. So this means that 1 is the very new movies, so that will be retrieved first, and 0 means that they are not very good movies. And everything after 40 years will have a minus 0.25. So this is your 3 period times, the 4-year, the 10-year, and the 40-year. And this is how all of our recency amortization functions looks like. So this is not really linear, but close to a linear one. And this is due to the nature of the system, how we handle time without being able to have to recalculate everything. So you can see the drop there. That's where you say that, okay, old movies, I don't care too much about it. Okay, so running queries. So he's a romantic guy. He's a water polo player. If you know water polo players, they're really romantic people. And so he wanted to search for a heartfelt romantic comedy. And you can see that, indeed, these are romantic heartfelt comedies. And but he decided that he had seen some of these older movies. So let's change the query. And you can see the recency weight is 3. You can throw in any number, so it will be normalized later. And indeed, everything is 2022. The data set ends at 2022. So yeah, we're good. Romantic comedies, 2002. Okay, so he said that, yeah, it's very good, but he doesn't really flex this on the title. He wanted to give more weight for the genre, because you can see that there are all kinds of drama and whatever. And then, indeed, it's more like a romantic comedy, comedy romance. So that's, yeah, it worked to an extent. But you can use an advanced query if you wanted to actually say which part should be what, not like just use the one search term. So in the previous one, you use this heartfelt romantic comedy thing for everything, for the genre and for the title as well. So in this query, it says like, okay, so the description should be met this one, but there should be something about love in the title, and it should be a drama, comedy, and romantic kind of genre. And there is no weight on recency, so don't care about when it was released. And so you can see that in the title, the word love is popping up, and drama, comedy, romance kind of things are also in the genre. Okay, so you can also use the weights to give different weights here. So you say, okay, I weight down the description, weight up the title, because I just want to see movies which title is love. You can get that. And then you say, I wanted to see, again, recent movies, recency 5. That will pretty much degrade everything else, but you will still see relevant results. But I will bet that these are in the order of release year and not anything else. The one thing you can also do is that you are not interested in new movies, but you are interested in old movies. So you say, I will give a negative weight for recency. And that's very interesting. So this is a vector space, right? And you can say, yeah, I wanted to have things which are closer to my instance or my query vector. But you can also do things which are very far from your query vector. So you say, no, negative 10. And indeed, you will see like very old movies. Okay, so this was basically the search part when you have a search terms. And the other thing is when you have a movie. So there's this White Christmas movie, and he really liked it, so he's looking for something similar. Obviously, White Christmas is very similar to itself. But he says, okay, so I wanted to have something which is more like family. So you can combine the two. You can say, I wanted to find something which is similar to this movie, but also have family in the description. And yeah, there are things like that, because otherwise it was all like band-related movies, because White Christmas is about forming a band. So we can go on and on. You can check this in the Superlinked repository. There are notebooks. You can run them in Colab. Just Colab quit on me, so I was not able to play with it. And just to summarize everything, so why use vectors? Because we don't want post-processing in recommendation. I mean, I personally don't like the idea that you fetch 10,000 something and then you recalculate everything. It's slow and it's not precise. You can skip something what is very important. So we can use soft filters instead of hard filters. You have seen it with recency, you have seen it with the genres. Put everything into the vector and do one query. And you can combine the vector spaces, so you catch multiple aspects of the same thing. You can do multimodal thing. You can have an image embedded and a text embedded, and you can search for both. And you can have the fine-grained recency and age control, what we developed. And one of the most important parts for me as an architect is that you take your definition of the vector, you take the definition of your queries, and you can bring them into production without having to rewrite everything into another language or something. So this is now, everything is in Python now, but we are building the system to be agnostic, so your executors or real-time systems can be written theoretically in any other language. So I think this is what we are trying to build. We are very excited about it, obviously. We just recently released the interactive part, so I would be very happy if you could check it out. Maybe put a star there to make our marketing department happy. Thank you very much. I'm open to questions, if you have them.
Thanks. I really love how you love to make people's lives easier, and this really combines the best of that world as well, so that's really cool. We do have time for maybe 1 or 2 questions. I'll grab this one.
Thanks for the talk. It's very informative and insightful. I have a question regarding the combining several embeddings into a single vector. What do you actually do with all those vectors? Are they all the same dimension? Do you add them all up, or do you make it a bigger vector?
So you make a bigger vector. You basically concatenate them. So that's when you wanted to combine different spaces. But when we aggregate vectors, that's the other way of combination, when there are multiple events and we wanted to aggregate them into one observation, basically, about the user. That's when we add, let's say, the vectors.
Hi, a very insightful talk again, and I really liked your point about, it can free up time for the data scientist to focus on the science and focus on the vectors. And as somebody that's very interested in data science, and now as of today, the whole vectors part, what advice would you give someone who's looking to kind of, get their start in, outside of like in my own spare time, just, trying to learn more about vectors, practice it? What advice would you give in terms of first steps if I want to, go towards that as someone with a data science mindset?
I think checking out this repository is also a very good start, but besides of that, I think so the hard part for us, even though we were doing data science for years and we have very good data scientists, is to understand how these vectors are interacting, how this normalization works, how these distances will work with the vector parts and all that. So I think if you start experimenting with embeddings and dig a bit deeper to see like how multimodal embeddings works, or how SBERT works, or all these more advanced vector systems, I think that's a very good direction if you wanted to like dig deeper and understand more about vectors.
Thank you very much. I appreciate that.
We'll take one more question.
Hi, thank you for the talk. You mentioned towards the start that you'd done some work on making the embedding more fast at search time when you're doing like a vector-based search. Would you mind elaborating more on how you can do like a lower latency embeddings at search time?
Yeah, so obviously we cannot like make magic, but what we can do is that a lot of systems works better when the input is batched, which means that you are not embedding one piece of text, but like 2,000, let's say, or multiple hundreds. So we have an online system which is deployed like a REST API or something, and then data is coming in. And obviously it's harder, especially in Python, to batch that data up real time and then like sacrifice some of the latency to get more latency, or so get lower latency. That's one direction. What you can do to speed it really up is have specialized hardware. But you don't want it to run your REST API on the specialized hardware necessarily. So what we are thinking about, or what we are designing, is that you have a service or a server dedicated for doing the inference, and it can batch up and it can optimize it for that hardware you are running it. So you can have one piece of expensive hardware doing all the expensive operations for you, and we optimize the usage of that. So that's what we can do actually, not much else. But there are exciting developments in that area with GPUs and everything as well.
Amazing, thank you.
Thank you very much again, George. Just for everyone's notice as well, the next talk is canceled, so feel free to go explore downstairs, but see you at 11 o'clock after break. Thank you again, George.